Hey, welcome to The Explainer. Today, we're going to tear a page right out of your high school physics textbook. We're going to ask a question that seems super simple, but it leads to one of the most bizarre and honestly beautiful truths in all of science. What is a proton actually made of?
Right, so let's just start there. What is a proton made of? I bet if you've ever taken a physics class, an answer just popped right into your head.
Two up quarks, one down quark. Yep, and they're all stuck together by the strong nuclear force. And that's it. A nice, neat little package. But what if I told you that this clean, simple picture is, well, basically a lie?
All right, so here's how we're going to get to the bottom of this. First, we're going to unpack that simple lie. Then, we'll use a physics analogy to get a grip on the totally bizarre force that's at play here, this self-charging force. We'll see how it acts completely backward, weak up close but crazy strong from far away. And then we're diving straight into the chaos, inside the proton's cauldron, to see the unseen dance that's holding our reality together.
So the whole three little quarks idea falls apart because the force holding them together, the strong force, it just doesn't play by the usual rules. And to really get how weird it is, we need to set a baseline first. We got to look at a force that actually behaves itself. So for that, let's take a quick detour into a world you're probably more familiar with, electromagnetism. This will give us the perfect analogy for how particles and forces are supposed to work, and it'll really set the stage for the weirdness that's coming.
Okay, so there's this key concept in physics called Bremsstrahlung, which is just German for breaking radiation. Now, it sounds complicated, but the idea is actually super simple. You take a charged particle, like an electron, and you make it accelerate, it sheds energy. And how does it do that? It spits out a particle of light, a photon.
And this isn't some weird niche thing. It's a fundamental rule of the game in quantum electrodynamics, QED for short, which is just the theory of how light and matter interact. So the rule is, accelerating charges radiate force-carrying particles. Got it? Good, because now we're about to see that rule get completely smashed.
All right, so keep that rule from electromagnetism in your head. Now let's jump back to the strong force. It's governed by a different theory called quantum chromodynamics, or QCD. And in the world of QCD, things get really, really strange. And here is where literally everything changes. In electromagnetism, the particle that carries the force, the photon, it has no electric charge itself. It's like a neutral messenger. It carries messages between charged particles but isn't affected by the charge. But for the strong force, the carrier particle, the gluon, is anything but neutral. It carries the very same color charge that it's supposed to be mediating.
And look, this is not a minor detail. This is everything. It's like if the particles that carry gravity were themselves incredibly heavy. Or imagine a referee in a soccer game who is also playing for one of the teams. The particle carrying the force is also a participant in the force. This just rewrites the entire rulebook.
So this self-interaction leads to a property that is so completely counterintuitive, it won a Nobel Prize. It's a phenomenon where the force behaves in the exact opposite way you'd expect.
You see, in the quantum world, the vacuum of space isn't really empty. It's fizzing with virtual particles popping in and out of existence. Around an electron, these particles kind of crowd around and screen its charge, which makes the electric force get weaker the farther away you go, like with magnets. But around a quark, the self-charging gluons in the vacuum do the complete opposite. They anti-screen the color charge, which actually amplifies it. And the result? The strong force gets stronger the further you pull away.
And this absolutely bizarre property? It has a name: asymptotic freedom. What it means is, when quarks are practically sitting on top of each other, they barely feel the strong force at all. They act like they're totally free. But the moment you try to pull them apart, that force grows and grows, almost infinitely, and just refuses to let them go.
And I know, this sounds like some wild theory, but it's not. We've proven it. Experiments in particle accelerators have confirmed it time and again. When scientists blast particles together at incredible energies, which is basically like looking at quarks from super, super close up, they see the strong force get weaker, exactly like the theory of asymptotic freedom says it should.
Okay, so we've got this insane cosmic rubber band of a force. So what in the world does that actually do to the inside of a proton?
Well, it means chaos. Pure chaos. If you try to pull two quarks apart, the energy in that force field between them, that cosmic rubber band, grows so immense that the field literally snaps. And when it snaps, that pure energy, following E equals mc squared, instantly creates a brand new quark and anti-quark pair right out of thin air. It's just mind-blowing.
And what that means is a proton is not just three quarks, not even close.
Sure, it has its 3 permanent valence quarks. Those are the ones that give the proton its identity. But they are drowning in a seething, chaotic cauldron, a sea of virtual quarks and antiquarks called C-partons that are constantly popping into and out of existence, all held together by a raging storm of gluons.
Now, here's the wild part. When we just leave a proton alone and look at it from the outside, this whole chaotic mess somehow organizes itself into a perfectly stable, coherent quantum state. It's this beautiful, self-regulating dance. But if we smash into it with another high-energy particle, we can actually kick one of those partons out. And at that moment, the coherence is broken. The dance stops, and for a split second, that chaotic inner sea is revealed to us.
So how do we even begin to map this chaos? Well, scientists use a tool called a parton distribution function, or PDF. The best way to think about it is like a series of incredibly high-speed photographs of the proton's guts. Each photo tells us the probability of finding a specific type of quark or gluon carrying a certain amount of the proton's total energy right at that instant of collision.
So, after all of this, what's the big takeaway here? Why does this journey from that simple textbook picture to this incredibly complex reality even matter?
You know, there's a quote from the research that just nails it. It talks about how the coherence of the hadrons enforces the recombination. What that really means is that a stable proton isn't simple at all. It's an unbelievably complex system that stays stable because of this constant, coherent dance of creation and destruction happening inside of it. And what this all means for us is that the fundamental building blocks of you, me, the chair you're sitting on, they aren't tiny, static little marbles. They are unimaginably dynamic, energetic systems. They are entire universes in miniature, governed by the strange and frankly wonderful rules of the strong force.
And that kind of leaves us with one last thought, doesn't it? If a single tiny proton is a roiling cauldron of virtual particles held together by a force that gets stronger the more you stretch it, what does that tell you about the true complexity hidden just beneath the surface of everything we think we know?